Well, hello, good morning, everyone. It's my pleasure to introduce our seminar speaker today, Dr. Omaira Gonzalez-Martin. Well, I would like to tell you a little bit about what Omaira has been doing during her research career. So actually, she started here at the IAC with a grant working with Jose Acosta on characterization of LIRIS, which is the near-infrared instrument of the William Herschel telescope. Then she did a PhD in the Instituto Astrofísica Andalucía in Granada on AGN from the X-ray point of view with under the supervision of Josefa Masegosa and Isabel Márquez. And then she did postdocs first at the University of Leicester in the UK, then in the University of Crete in Greece, and then she went back, she came back to the IAC, and she had a postdoc under the group, with the group Estallidos, and she developed the reduction pipeline of the Canary Cam instrument on the GTC. So she's now an expert on X-ray and mid-infrared studies of AGN in particular. And Omaira is one of the bright researchers that Spain has lost, unfortunately, because she is now a permanent staff at the Instituto of Radioastronomía and Astrofísica of Morelia in Mexico. But she works with us, so we have the opportunity to continue with collaborating with her. And today she's going to tell us about her last work on AGN torus models. Thank you, Mayra.
Thank you, Cristina. I would prefer to say that Mexico won rather than Spain lost. Well, it's always a pleasure to be back. It's a long time collaboration with people in the IAC, with Jose Miguel, or Jose and Cristina, and many others. I'm going to talk to you today about a work we just got published about the AGN dust models. We published this work in 2 companion papers, and it's a good example of the kind of collaboration that we do from Mexico, mainly from my group, and from Spain, some of them from here from the IAC, and some others from the IAA, and also I have one colleague from Korea, which is Mariela Martinez Paredes, who was actually a postdoc of mine in Mexico, but is currently in Korea, still working with us. This is the outline of my talk. I know most of you may be bored about the main concepts of AGN, but I think it's worth for students. I will talk a bit about that, about AGN families, AGN components, and the unified model, and then I will go directly to the topic of this talk, which is the AGN dust, why it's important, and why, how can we infer its properties, and then I will focus on the way, the technique that we used in these 2 companion papers, which is mid-infrared spectral fitting to try to infer the properties of this dust using several AGN dust models. And for that, we use synthetic spectra to try to understand if we can differentiate these models, and also to try to see if at which level we can infer the parameters of these models. And we also use Spitzer real data to try to understand which of the model is best suited for the data. And at the end, I will give a short summary of the results. If you want to have a definition of what an active galactic nucleus is, I will say it is a bright source at the center of the galaxy, which can be much brighter than the galaxy itself. In some cases, you just see a point-like source because the galaxy is completely outshined by the nucleus. This brightness and also the fact that the object is variable makes it impossible to explain with stellar processes. You have to claim the existence of an accretion process that fits a supermassive black hole. And these sources emit at all wavelengths. Since they were discovered in the 70s or 60s, many classes have been found in different ways with different observational techniques. I'm not going to go into details all of these classes, but just a few of them. From the radio point of view, you can classify the objects as radio quiet or radio loud, attending to the ratio between the continuum emission at radio frequencies and optical emission. Essentially, this classification gives you the idea on how is the preponderance of the jet over the entire volumetric luminosity of the source. You can also classify the objects at optical wavelengths through the spectrum, and this is a very well-known classification, probably the most famous one, which is based on the idea, based on the study of the permitted lines in the optical spectrum. If you see a narrow emission line, then you will classify the object as a type 2. If you see broad components in these permitted lines, then you will classify the objects as a type 1 AGN. And then there is another classification attending to the preponderance of the nucleus versus the host galaxy. If the nucleus is much brighter than the galaxy, then you will classify the objects as a high luminous AGN. If the luminosity of the nucleus is comparable to that of the galaxy, then we classify the objects as intermediate luminosity AGN. And if the nucleus is much fainter than the galaxy, you will classify the object as a low luminosity AGN. I've been working a lot about this class in particular because they might be the link between AGN and non-active galaxies. But in this case, I will be talking about all the range of luminosities. Okay, attending to all these properties that are derived from different wavelengths, as I said, AGN emit all over the entire electromagnetic spectrum. We have found several components. The first one for sure is the supermassive black hole with 10 to the 5 or up to 10 to the 10 solar masses. And then surrounding this, there is an accretion process, which is simplified as an accretion disk. Sometimes it's more complicated than that. It is a tiny portion of the galaxy. And then outside of that, you have what we call the broad line region and the narrow line region. The broad line region is conformed by clouds, which are close to the accretion disk. They are moving fast because they are feeling the dynamic of the supermassive black hole. And the velocity dispersions can reach up to thousands of kilometers per second. Further away, you have the narrow line region, which is also conformed by clouds. And this region can reach velocity dispersions of hundreds of kilometers per second. In some cases, you also have a radio jet, can be tiny, of the sizes of the accretion disk itself, but it can also reach a very large distance from the AGN. It can reach up to several times the galaxy itself. I have left until the end the component, which is the dust, because it's the main topic of this talk. What we know about these dusty components might be very tiny because we haven't observed it so far. And the way we can get information about this dust component is going to the mid-infrared, because the emission that is attenuated by the dust at optical and UV frequencies is re-emitted by dust at the mid-infrared. So studying mid-infrared will give us hints on this component. The last slide about about AGN itself is the unified model. It's something that we all put. This is one of the most updated version of this model. Essentially, what we believe is that many of the classes that we observe can be understood as a single object, where we have in the center the supermassive black hole surrounded by the accretion disk, and then a plethora of clouds. Inside of that sublimation radius, you have clouds free of dust. Outside, a mix of the two. Along the equatorial plane, you can distinguish this component because it's more or less stable, and this and it's conformed by clouds with gas and clouds with dust. And in the polar direction, we believe there is also an outflowing wind composed by gas and dust. And these outflowing winds can be seen as a hollow cone in the sense that if you observe it from inside, you can reach the inner parts where the accretion process is. And in fact, you can clearly see the inner clouds where the proton region is located, and you will classify the objects as a type 1 AGN. If you are not so fortunate and you observe the object along the equatorial plane of the disk, you must certainly observe a lot of clouds along the line of sight, so you won't be able to see the inner components, and you will classify the object as a type 2 object. So there are two main parameters in this model. One is the dust, and the other thing is how you see that dust, the viewing angle toward the dust. But how do you think is the dust arranged? I was trying to give you some subliminal messages along this first part of the talk, just in case you didn't catch it. Here's another one, torus. We've been believing that this structure is a torus since almost the beginning, because the pioneers in these kind of works assume, partially because it was the simplest thing to assume, but also after that everybody was following the fashion of the torus, and we were trying to look for this torus for many years. And in fact, if you go to the literature, and in particular if you go to the books that students study, what you are going to see is this kind of unification models. In all the cases, they assume that the torus is that the dust is a torus structure. But we actually don't know. If you ask me what we know about the dust, I repeat what I said before. It must be very little, because we haven't observed it so far. And this is because in mid-infrared we don't have enough spatial resolution and enough sensitivity to do an image of this torus. Probably one way to solve this issue is to go to submillimeter wavelength, because with ALMA you will have enough spatial resolution and sensitivity to observe at least the nearest objects. Basically, torus peaks at 20 or 30 microns and then goes down to submillimeter wavelengths. The problem here, and this is something we reported in this paper, it's a paper done by our group and led by Alice Basetto. The problem is the contribution of the jet to the submillimeter wavelengths in the continuum. If you do the numbers, you end up knowing that in most of the cases the jet dominates the submillimeter wavelengths. Only the bigger, denser, and most luminous tori will be observed, but these more luminous objects tend to be quasars, which tend to be at higher redshifts, which so in this case you won't have the spatial resolution enough, even with ALMA, to observe the tori. So it's a very tough solution, still working on it. We have a few candidates that might be better to try to explore if we can detect the torus, make an image of the torus at the submillimeter wavelengths. But it definitely cannot be done for a large collection of objects. Another way to do it is mid-infrared interferometry. This has been done for 10 to 20 objects. An interesting result that they got is that there is a non-negligible fraction of the mid-infrared emission that comes from a polar dust. The problem here is that you need the object to be very, very bright, so you are biased toward the brightest objects, and also that you need to assume a model in order to get your results. The technique I'm going to explore here is the mid-infrared spectral fitting. This is something now in our group we've been doing for a long time. Christina has done a lot of work on this topic. In this case, what most of these papers have done is to take a model called clumpy torus model by Nenkova and collaborators, 2008. And what they did is to produce this code, this nice code that is actually is very good at obtaining parameters from spectral fitting. I'm sorry. And infer some parameters of these objects in several classes of objects using this technique. This is good, but we know there are many other models, not only clumpy torus model. Here I'm listing a few of them. They are the 6 models with available, publicly available SEDs, so we can play with them. The first one is the smooth torus by Fritz and collaborators. I'm trying to explain you these models because I'm going to be using them along the talk. Then the next 2 models are 2 clumpy torus models by Nenkova and collaborators 2008 and Hoenig and Kishimoto 2010. Then there is a smooth plus clumpy torus that can also be seen as an outflow by Siebenmorgen and collaborators 2015. 1 year later came this paper by Stalevski and collaborators 2016. In this case, what you have is a combination of a smooth plus a clumpy torus model. And the latest model is done by Kishimoto and Hoenig and Kishimoto 2017, where they model the dusty structure as a clumpy torus, as a clumpy disk plus a wind. As you can see, you can differentiate this model by the dust distribution. Some of them are smooth, some of them are clumpy, and you also have a combination of the two. You can also distinguish them from using the geometry that they use. Most of them toroidal, as I said, that was an easy assumption, but some of them explore also winds. And also the dust composition changed from model to model. And of course the parameters involved change for all the models. The only parameter that is common in all the objects is the viewing angle. And even in that case, the assumption that they made for the convention of the angles changed from one model to another. So it's a really tough work to be done. If you ask me about the dichotomy between clumpiness and smoothness of the distribution, we know that we started assuming that the distribution was smooth, that was for simplicity, and then at some point people realized that it was very tough to make a smooth torus to be stable, because if you want to make a thick torus, you need to assume that these particles are moving fast, and if they are moving fast, they are gonna be heating up the medium, and then they will reach a temperature where they destroy the dust itself. So a solution for that was assuming clumpiness, and however, there are several observational walls favoring in the smooth models instead of the clumpy models. I'm showing you here one of them, which is from Mendoza Castrejon 2015. What they did is to take Spitzer spectra and measure the silicate features at 10 and 18 microns. They measured the strength of these silicate features, and they put it in a plot, comparing with smooth and clumpy models. And what they found is that, at least for few objects, they needed to assume a smooth distribution instead of a clumpy distribution. Another point in favor, and this is a talk my student Donna He gave a few weeks ago here. She was trying to explain both X-ray and mid-infrared emission using these models, and she found that, at least for this object, that the smooth distribution is better than the clumpy distribution. But it's not only that we don't know the distribution, composition, etc. It's that also that the dust distribution could change along the duty cycle of activity of the agent. In favor of that, Christina did the work where she compared type 1 and type 2 dust structures, and found that they definitely show difference on the properties of the dust. for ciphers at least. And then Mariela Martinez-Paredes, and this is a paper 2017, she included quasars and also saw difference on the dusty structure when compared with ciphers. I extended this kind of work toward low luminosities, and in this case what I did is to make an average of the spectra obtained with Spitzer for different, essentially for different volumetric luminosities. And what we found is that you can fit the highest luminosities very nicely with clumpy torus by Nenkova, but then when you move toward lower luminosities, there is a limit below which the continuum doesn't look like, the continuum cannot be fit with these clumpy torus models. And there is another limit below which there is not signatures of the dust at all. This is what we call the disappearance of the torus, and it's something which is expected by theory. Okay. Let's see if it works. Okay. So with all this in mind, our idea was to study AGN dust models, and for that we wanted to explore current and future facilities. In particular, we explored Spitzer. Spitzer is going to give us a wide range of wavelengths, but the spatial resolution is not so good, which is bad, because then you might have a host galaxy dilution in your spectrum. For that, GTC is much better, but then the spectral coverage is smaller, and for sure what is going to be the best is James Webb, which is the one is going to give us a high spatial resolution and good coverage. In fact, with James Webb, you can observe that near-infrared and mid-infrared spectra of these objects until very faint sources. So the main objectives of this work was to try to see if we can differentiate these 6 models I was speaking about. Also to try to understand how good we could be to estimate the parameters of these models, and how it depends on the spectral range, sensitivity, and host galaxy dilution. And we also wanted to see, with the current data that we have, which is essentially Spitzer spectra, if we can tell which of these models was preferred. Most of this work was done through synthetic spectra, and let me show you just a diagram of the process that we made for this synthetic spectra. I know it's a mess, but it's what we did. Hopefully I will show you just the idea of how we proceed with the synthetic spectra. Essentially, we studied four instrumental setups, were GTC Canary Cam, Spitzer IRS, James Webb at only mid-infrared with MIRI, and then James Webb including near spec, and therefore having near infrared and mid-infrared at the same time. We also explored 4 sensitivities, which are equivalent to signal-to-noise ratios between 5 to 7 and above 100 the signal-to-noise. And I went for this instrumental setup. As I said, we explored 6 models. There you have them. And for each of them, we produced 1,000 of synthetic spectra using random numbers for the parameters. We also wanted to check if this number was enough to explore the whole parameter space. For that, what we did is to also use a fixed step for the parameters. So in this second approach, the number of synthetic spectra depends on the number of parameters that each model has. It can reach, in the case of Hoenig and Kishimoto model, which has 8 parameters, it can reach an additional 6,000 synthetic spectra. We took these models and fit them to their own, we took these synthetic spectra and we fit them to the same model, but we also fit them to the other models. We fit them to the same model to try to understand at which extent we could restrict the parameters. and we fit it to the others to see if we can distinguish this model from the other. The second step was to try to study the host galaxy dilution, and for that we included stellar contribution and interstellar media contribution and a combination of the two at different levels. And again, we fitted them to the same model that we use, and in this sense we could evaluate if the parameter determination was getting worse when we added some dilution, galaxy dilution. Altogether, 1.5 million fits, which means more than 3 months of computing in up to 5 servers with a range of between 8 and 64 cores each. So a lot of work, but definitely I believe was worth it because we found very nice results. Let me show you some of them. The first thing that we wanted to explore, because nobody had done it before, was to try to understand if this model can be distinguished using diagnostic diagrams. For that, I computed 3 slopes and defined as in this way. The first one is what I call near-infrared slope, which is, I name it like that because it's the closest to the near-infrared frequencies. Then one in the middle of the mid-infrared, I call it mid-infrared slope. And then the one closest to the far-infrared, that I call it far-infrared slope. Here I'm showing you the plots, the diagram between the alpha mid and alpha near for all these, all the models. The blue box that you are seeing up there is repeated in all the plots. It contains most of the points of this smooth torus model by Fritz. It is just something to guide the eye to see the difference between the models. One thing I want to show you is that there are models that cannot be distinguished within these diagrams. For instance, the model, the clumpy torus model by Hoenig and Kishimoto 2010, and the clumpy disk plus wing model by Hoenig and Kishimoto 2017. These 2 models are using the same radiative transfer code and also share some most of the parameters indeed. I believe that's the reason why they share the parameter space. Another one is the comparison between the smooth torus model by Fritz and collaborators 2006 and the smooth plus clumpy torus model by Stalevski and collaborators 2016. These 2 models do not share the radiative transfer code. What they share is the geometry. The only difference between the 2 is that this one is including clumpiness, while this is not. But the geometry is exactly the same, the parameters are exactly the same. If you go to the other diagram, the one exploring far infrared versus mid infrared, again, these 2 are similar. These 2 are also overlapping, but not so similar. Here, what I believe is that Stalevski and collaborators use the same prescription, the same geometry, and the same parameters, but they do not evaluate the same range for the parameters. This is much narrower range for some of the parameters and yield to a different locus compared with the smooth torus, which covers a much wider range for some of the parameters. Definitely you can differentiate among the models, at least for some of them. For instance, these 2 models, they tend to have higher far infrared slopes than the rest. So it can be useful to try to understand what are the difference between, what is the best model based on these diagrams. Another way to see that is using a chi-square statistic. If you get this synthetic spectra fitted to all the models, then you get a chi-square for each of the synthetic spectrum. What you are seeing here is the distribution of this chi-square. I have to tell you that it's in log scale. For instance, let me show you. This is when you use the synthetic spectra produced with the clumpy torus model by Nenkova. When you fit it to its own model, you get a very good fit. When you fit it to any other of the models, the chi-square statistic is much higher, which means that the model is not good at describing this synthetic spectrum. And this is interpreted as it's saying to us that we can distinguish the Nenkova model from any other of the models. Same goes for many other models. The ones that that cannot be distinguished are these two, for instance. If you produce the clumpy disk-wind model, synthetic spectra using this clumpy disk-wind model, and then you try to fit it to the clumpy torus by Hoenig and Kishimoto 2010, you get very good fits, meaning that you cannot tell which one of the two it is. And if you do it the opposite way, you produce synthetic spectra using this model, definitely you can fit it with the other one. Something similar happens when you compare the smooth torus model by Fritz and the smooth plus clumpy torus model by Stalevski and collaborators. In this case, if you produce synthetic spectra using the smooth plus clumpy torus model, you can fit many of these SEDs of these synthetic spectra using the smooth torus by Fritz. The opposite is not so true. If you fit Fritz, you are not so good at fitting these synthetic spectra using the Stalevski and collaborators models. Again, this means that probably the parameter space is not the same. It's much larger in the case of Fritz, and that's why some of the models, some of the synthetic spectra are not well fitted with the other model. But what happened with real data? When you put the real data on top of these diagrams, you get interesting results. For instance, well, what we did is to take this Spitzer spectra of 110 AGN and compute exactly the same slopes and put them into the diagrams. What you are seeing here is alpha near versus alpha near. And the main result is that you can nicely explain this data with the clumpy torus model by Hoenig and Kishimoto, or with the clumpy disk-wind model by Hoenig and Kishimoto 2017. For the rest of them, the main failure is that it cannot explain near infrared slopes. But what happened with the other diagram? The opposite. Now you are not able to explain mainly the alpha fear. For this diagram, are better the Stalevski and collaborators 2016 model, the smooth plus clumpy torus model, or the smooth torus model by Fritz and collaborators 2006. Another thing I want to show you here is how many SEDs are lost, in the sense that a lot of SEDs do not explain any data. And this can be seen here and there, or in the other, in the other plot even better. A lot of SEDs that do not explain any data. What I believe is that modelers should rethink on the parameter space that they use. And with that, we could get much better fit to the data. Also, as I said from the very beginning, we wanted to explore how good we were estimating the parameters. For this, we went back to the synthetic spectra. What I'm showing you here is the average error per parameter. Each circle is a different model, and each quarter of the circles is a different instrumental setup, each parameter in a different angle. I know it's a complicated plot. And each color represents different signal-to-noise ratio. The highest signal-to-noise ratio is the cyan, while the green is the lowest signal-to-noise ratio. The main result is that in most of the cases, except this one, Hoenig and Kishimoto 2017, we can recover the parameters within 15%, which is this dashed circle here, except for the lowest signal-to-noise ratio. And we cannot obtain the parameters in this case because this is the most complicated model. It assumes a disk plus a wind. It has 8 parameters. So definitely in the spectral fitting will never give us the parameters of this model. We also explore stellar dilution, as I said, also explore interstellar medium dilution, and also the combination of the two. And the main result is that still we can recover the parameters of the model as long as the the contribution of this host galaxy is less than 50%. But what happened to real data? In order to explore what is the contribution of the AGN dust in our Spitzer spectra, we explored 4 baseline models. The first one is just the AGN dust model, and then we include stellar, interstellar medium, and the combination of the two. We did some statistical tricks to try to understand which was the best. And after that, we explored in how many objects the AGN was dominating the mid-infrared spectrum. And this is what I'm showing you here in gray bars. As you can see, it depends on the model, which is not very good. And also, it can range between, the percentage of objects can range between 75 down to 50%. So in a lot of objects, the Spitzer spectra is including more than 50% of host galaxy. And that's the main reason why we need a high spatial resolution in the future. And this is why James Webb is so important for us. Another thing that you can derive from this plot is how many fits that you get when you only use the AGN dust model. This is the black bars that I'm showing you here. As you can see, it ranges from up to 25% and down to 0. If you try to fit these Spitzer spectra, even those that are AGN dominated, according to our criterion, in all of them you need some extra contribution to fit the data. If you add this extra contribution, you end up with the other bars, which are brown or something like that, or red. And this is telling to us that the most preferred models are these two, the wind plus disk model by Hoenig and Kishimoto 2017, and the clumpy torus model by Nenkova and collaborators 2008. Another interesting results comes when you split this diagram into classes, in optical classes in this side, in luminosity ranges in this side. What I wanted to show you is that a Hoenig model, the disk plus wind model, is totally preferred by CIFER ones and totally preferred by high luminous objects. While when you go down to lower luminosities or type 2 objects, you end up having a very good fit also with Nenkova and collaborators model, this clumpy torus model. The idea is that there is a difference according to the luminosity. For high luminosity, the dust must be arranged in an outflow wind. When you go to lower luminosities, you end up having a large portion of the objects arranged in a clumpy torus distribution. We also wanted to explore the parameters. I'm not going to show you almost nothing about this. The idea was to try to do this. What we did is to infer posterior distribution per each parameter. This is just an example of one of the objects using one of the models. This is the clumpy torus model by Nenkova and collaborators 2008. As I said, I don't have time to show you all the figures of the paper. There were 20 pages each. But let me give you a list of the main results. We confirmed with real data that the parameters can be roughly restricted to the 15% of the parameter space for all the models at Hoenig 2017, and this is the result of a much more complex model. The resulting parameters depend on the model used. This goes even for the viewing angle, and this is something to take into account in the future when you are trying to fit the spectra to this model. At least you need to try several of them to be sure that you are using the preferred one, and therefore you are estimating the parameters that are meaningful. Many objects tend to show upper or lower limits for the parameters. This might suggest that the parameter space should be revisited in order to get improved fits. This is something we also understood from the diagonal fit diagrams. And the most robust quantity is the total dust mass, which is consistent with the same value irrespective of the model used. This is not the case, not even for the covering factor, which depends on the model. And I think what is the nicest result coming from this analysis of the parameters is that the outer radius of the dusty structure inferred from the smooth model is twice smaller than the inferred from the clumpy torus model, and this is contrary to the general assumption. One thing against this smooth torus model were that the people believed that the tori that you were obtaining were much unrealistically large. And when you take a whole sample of AGN and you feed to smooth and clumpy, you end up knowing that the smooth torus model always give a smaller outer radius for the torus compared to the clumpy torus model. About the complex of the mid-infrared spectra, what I'm showing you here are the residuals when you get these 100 of spectra and you try to fit them to each of the models. As you can see, there is a lot of room for improvement, a lot of dispersion in these residuals. In particular, in the far infrared, the slope is not matching in many of the models. Near infrared is the same, close to the near infrared is the same, and also the silicate features they are not very well fit. You might think that this is due to the spatial resolution, but then you go to the highest spatial resolution. This is something that my student, Cesar Victoria Ceballos, is doing. He's taking the only object that has been observed in both N and Q band, which is NGC 1068. And he's trying to fit to several models, and none of the models are able to fit both the N and the Q band at the same time. One trick you can do is to try to vary some of the parameters, and then you get a very good result. This is telling to us that the dust is much more complex than the models. We are currently working on using radiative transfer code squared to try to produce a better solution, a more complex scenario to try to fit these two spectra at the same time. But we are wondering if this is the only case because it's the only one we have observed, or because this is just a very complex object. We all know that NGC 1068 tend to show the weirdest things. But in order to understand that, we need more data, and of course, right now, the only solution is CanariCam at GTC. We got approval on one proposal to observe a few bright AGN in the Q band for those that we already had N band. So we will. It seems that the CanariCam is working properly. So hopefully we will have at least a few objects to test if this is the only case, or is a general behavior. Because if it's general behavior, models should be working hard to try to explain them. Of course, one of the main purposes of this analysis was to prepare us for James Webb. As I said, James Webb is the only one that will give us spatial resolution and sensitivity enough to do this kind of jobs. I'm working in several things around James Webb. One thing is that I'm organizing this James Webb Master Class in Mexico 2020. It's going to be in February. It will be held in the Instituto Astrofísica in Mexico City, but it will be broadcasted to other places. So if you are interested in attending, please let me know. Another advertisement is the Reunión de Extragalactica in Mexico. This is something that this is the second time we organize in Morelia. It's going to be in December. It's a good opportunity to meet extragalactic people. If you are interested in coming, also tell me. And let me finish with my group. I'm very proud of my group because it started with me 5 years ago alone. And now we are 9 people, 6 with photos and 3 without photos because they are very new members. I don't have a photo from them. I'm always looking for new members, permanent staff, postdocs. We have postdoc opportunities every 6 months. Also have opportunities for students. It seems that I'm going to be the new person in charge of the postgraduate from now on. So if you have students that want to come to study with us in Morelia, please also contact me. And that's all. I give you here my summary and a nice picture of a non-existent torus.
Thank you very much. It's working. Yeah. Thank you. Questions for Omaira? Hola, hola. Okay, just checking.
Okay, I'll start. Nice talk, Omaira. So I just wanted to make a comment because you were very pessimistic about what we can do with ALMA.
Yeah.
We have discussed about this, no? But I have to say that it's true that it's difficult to constrain the dust in the submillimeter because of the non-thermal contribution.
Yeah.
But in molecular gas, using different lines, you can get very good constraints on the torus, on the size of the torus, gas mass,
sure,
etc.
sure,
So
sure.
there is still a lot of things that we can do with ALMA. Although dust is more complicated, but they should coexist.
I should
right?
have clarified that, yeah, definitely. I put in the talk dust everywhere.
But I agree with dust.
It's quite tough, no? But definitely molecular gas, there's a lot of work to be done there.
Can I? And another thing that I was wondering, so looking at the plots, no, of the different models, no, how they reproduce the spectral slopes or the real, even the real data. So it's clear that it's parameter space that the models are not covering, and we need to have them in order to reproduce the data. And something that it's also evident, and that might explain why sometimes the smooth torus model works better than the clumpy, is that with a clumpy model, with any of the clumpy models, you cannot fully reproduce the smooth model, no? Because in principle you should be able to do it if you just put more clumps.
Yeah, but then it's a matter of the parameter space because
Exactly.
Well, Nenkova model explores. I don't know. You know better than me, but the maximum number of the equatorial clouds is
15,
15.
no? Which is nothing, no?
Yeah.
That means that, I mean, if
So,
what I
so
mean is,
you think that we could do well, modelers should do definitely they should do an effort on trying to see what happens when they explore a different range, if they manage to get better into the
because
the
ideally
comparison.
with one of those you should be able to reproduce more or less, no, the smooth, and at the moment you can't.
Well, it's a matter of knowing what happens when you add clouds. Do you think you are gonna end up filling this gap, or I don't know? Because here the problem is the alpha mid, but in the other one, the problem is basically is mainly alpha near. And for that, well, indeed, these two models are very good in alpha near, and in fact, they are very well aware of that because they were trying to solve this issue that we couldn't fit the alpha near, but then they miss alpha here. I think it lacks of a proper comparison. No?
But what you meant is that maybe if you had a model with an infinite, as high as possible number of clamps, you could fit everything. Or what?
No, I think now on the best thing is to use this kind of approach where you can actually compare the smoothness with the clumpiness. No, why to assume clamp or smooth if you can do both? No? Yeah.
So yeah, I'm just curious about this. When you're considering these models, I understand that these models take into account a different dust geometry. Do they take into account variations in dust properties, in the composition of the dust?
Yeah, well, they explore, there is, I think one or two that explore several, but in the models I'm using, they only provide the SEDs for one single composition, but definitely each of them use a different one. So you can somehow explore the compositions if you manage to understand what is the role of the composition
So
in the
my question is
resulting
then,
SEDs.
so my question is, if you have that, could you expect some sort of systematic in the sense that perhaps the smooth model will work for a certain dust composition, whereas the clumpy one will work better? Because that's what happens with stars as well. You can change both and get the same thing.
And also protostellar disks, they are exploring different composition, and the composition is the whole story. definitely we need to explore composition too.
And the other thing is, when you're comparing this, I like a lot these star diagrams where you actually put the different values of the chi-squared. One question I have is, I find it curious, no, the one where you have the star, basically you compare different models at different angles. The polar one, yeah. I think it might be, yeah. This one, yeah. So I'm curious because if I understood correctly, the last one that you have there on the bottom right, that's supposed to be the most complex one. So in principle, would you expect the most complex one to be the one that gives you the better fit? So could it be a problem of the algorithm not finding the best fit properly because it's too complicated? So if you want the parameter space is too complex?
No, because the data are not good enough to restrict the parameters. You have the same spectral range, and then you have a 3 parameters model. It's much easier to restrict them than 8 parameter model. That's the whole story here. Definitely, this is the one is working better.
And would you say
it ends up being the best model, but the point is that I cannot tell you the parameters of the model. I can tell you this is the best.
And could you actually choose one that is the better one taking into account the complexity? Sort of if you divide this by the number of parameters, would you get an ideal one?
Okay. I didn't do that.
Interesting to see. Thank you.
Very nice talk, Omaira, as always. Could you go back to one previous? That one. Have you thought about the outside dots? What would they represent?
These,
what type of sources? No.
This one?
Yeah.
Round parameter space. I'm pretty certain about that. They cover outer radius of the torus that will mean that we should observe them. So if you cover an outer radius of the torus which is 100 parsecs, we have enough spatial resolution to tell that this is not true. So many of them should be due to that.
More questions?
Yes, I'd just like to ask you about your illustrations of the torus, and very nice moving artwork. Did you make that yourself?
Which one? In general?
I've seen many that I loved.
I took it from Google, Googling.
Okay.
I put torus and plenty of them appear. I had to choose, you know, the most impressive ones, no?
But the rotation and the movement of those are...
It's a gift.
Yeah, no, I know. No, I wonder if they have a physical meaning. They are supposed to be like that, or because they were moving, you know?
No, it's just to impress people. No, no, it was just capture your attention so you get my point that everybody was thinking was a torus.
More questions for Omaira?
Omaira, do you think that if you include the optical or ultraviolet, will you be able to constrain the parameters somehow? Because I think you have a lot of dust. The dust will block part of the light. So depending on the configuration, it will block in a different way.
Well, the problem there is that everything attenuates optical, not only the torus, also any dust lane that comes along the line of sight, and then you have to add more. I didn't say it, but I was adding, let's see if I go back to the models. I was adding extra attenuation. In the optical, you will dominate it by this the extra attenuation. So it won't give information about the dust of the AGN, but the dust around.
And the work you present, well, your student presented a few days ago, about the X-ray. Can you use the same information? Share the information to restrict the parameters? Yeah,
that is her PhD goal, to enlarge the sample, to study all the large sample of agent, not only that one that was showing you, don't remember where it is, but I showed you in the beginning a slide showing Donaghy's work. She's trying to compare X-ray and mid-infrared to try to restrict better the parameters, and this is working nicely, at least for the single object she analyzed. But the point is now to compile a large collection of objects and then study several models at mid-infrared, also several models at X-rays that might not agree to each other, and try to see if we can tell that the same structure is produced in mid-infrared and X-rays, and if that is the case, if we can restrict better the parameters using both wavelengths. Yeah. Hopefully in 1 year she will come here to show you the results.
Any other question? Let me check if we have questions in the email. No, we don't. So thank you. Yes, sure.
So I think this is the last seminar that Adriana is organizing as a seminar organizer. So I think we should ask not only Omaira, but also Adriana for all the work that she has done.
Thank you very much. Omaira is going to be here until the end of the week, no? Are you coming to the ISC?
More or less.
Well, if you come, where can they find you?
Well, I don't know, in the library probably.
In the library, okay. You can talk to her if she comes. Thank you very much, Omaira. Thank you, Cristina. Thank you.